So we'll pick up kind of where we left off last class, talking about like weighted means, weighted variances. I wanted to mention kind of if we go on our assignments here. So I put that the first Connect and first Excel assignment are now up. For that Excel assignment, I think I even kind of have in the description here. You know, you can kind of do it one of two ways. So, you know, you have to upload your Excel file where you've done all the work in Excel, right? So you shouldn't be doing anything by hand. You should be doing all the work for these Excel assignments in Excel and then uploading that file. However, some of the questions might require a written response, right? So I think on this one, let's see if this pops up for us here. Oh, it's just taking some time. I think for C, no, for like B here, it kind of is asking you for a written response. So if it's easier to do those written responses, you know, if I'm trying to do this in Excel, if I just type a bunch of words here, kind of extends across multiple cells, but then if there's something in its way, I can't see everything. Now I can always see everything up here when I click on it, so it's fine. If you want to type out your written response in Excel, I can still see it, but a lot of people, I think it's easier and it's easier to edit if you just want to do those in Word and then upload your Word and your Excel file. That's fine. You know, as long as you upload multiple files. In fact, you know, uploading a separate Excel or a separate Word file is a lot easier than if you do all of your work here and the short answer ends up over here and, you know, I don't see it or something like that. So I would suggest probably the easiest way to do those written responses, just type them up in Excel, or sorry, type them up in Word and then upload both your Excel and your Word file. Okay. All right. Any questions for me before we kind of get started today? Anything related to the homework or anything like that? We're okay with this? All right. So last class, just kind of review here real quick. We talked about a weighted mean, right? We had our equation where we went through every observation, took the weight, and multiplied it by that observation's value for x, added those up. Once we did that for every observation, we added them all up, and then divided by the sum of our weights here. So we can do the same thing for the variance. We can still find those deviations from the mean squared. It's just now we have to weight them by whatever the weights we have associated with that group data is. And then once again, instead of dividing by n, divide by the sum of our weights, okay? So that's where we left off, right? So we had some of these examples that we worked through. So what if instead I had something slightly different? So I still have group data, but remember we were building those histograms and doing all the frequency distributions? What if that's the only data I can observe? So let's say we had some product here that was given a satisfaction rating by consumers. Now, there were the individual responses, like somewhere somebody could observe about 50 different responses and exactly what somebody responded, but they then grouped it and put it into these bins, right? And there were, say, 4 people or 4 observations that gave it a satisfaction rating between 36 and 38. There was then 15 people who gave it either a 39, a 40, or a 41, so on and so forth, right? But this is the only data I can observe, right? So, you know, how do I come up with kind of the mean for a data set like this, right? Well, I can think about these frequencies I can use as my weights, but what values do I use for this variable I'm interested in, which is the satisfaction rating, right? What's the mean satisfaction rating here? Well, if I looked at this data, where would I guess, right? And we'll talk about exactly how we compute it in a second, but where would you guess around what value would the mean be? I'm just looking at this. There's a couple different things you could say that would make sense. Somewhere around 42, 43. So why are we thinking even in the 40s here? Well, remember the frequencies are our weights, and this is telling us the majority of the values are in this range, right? Or just above it, sorry, just below it and just above it, right? Not very many observations far from that point. So if I had to guess, I don't know, 42, 43, 44, somewhere near one of those values. Right? How can I actually calculate it though? Well, we don't have a value, we have bins here, right? We have ranges of values. So all I'll do is use the midpoints, right? So between 36 and 38, I'll use the midpoint of 37. Between 42 and 44, I'd use the midpoint of 43. Now that I have all those midpoints and I have my frequencies, which are my weights, it's just like we were doing before the weighted mean. Take that midpoint of 37, multiply by the weight or the frequency of 4. Do that for every single observation. Once I've done that, add them all up. And then finally divide by the sum of my weights, which here my weights are frequencies. So just divide by the sum of my frequencies. So that's going to look something like this. Right? It's really the exact same process we did last class. It's just now our weights are specifically frequencies, and we don't have one value. We have a range of values for each one of these groups or these bins, so we have to use this midpoint. Okay? But procedurally, it's exactly the same. Okay? Now, one thing that we talked about when we were doing frequency distributions, if I add up those frequencies, what should they add up to? If every observation is counted in at least one of these bins, the frequencies should add up to just the total number of observations. Now, it's a little weird here because I can only see this data. The person who grouped it was the only one who could actually see the original total number of observations, right? But I can actually reproduce that or figure out what that is by adding up the frequencies, right? So this would be like in the COVID data, when I grouped it to the number of states that had cases in between certain ranges. Well, there was originally 50 states. I wasn't able to see that data set. I'm only seeing kind of that frequency distribution. But once I add those frequencies up, it should be the number of observations in that sample data set, right? So the sum of the frequencies is the same as the original number of observations in the data before it was grouped, right? Any questions on that? We'll go through the example here with some numbers in just a second. Now, the variance is going to be pretty much what we did last class with the variance. We're still looking for the deviation from the mean squared. It's just now we have to use these midpoints, right? So once I find all these deviations squared, once I find the deviation squared, I then need to multiply it by that group or that bin's frequency, right? Multiply it by the weights that we're using. Do that for every observation, add them all up. And now, because if we're dealing with sample data, instead of dividing by the sum of the weights, which here are frequencies, so you can think about this as we would actually take the sum of the frequencies, which we know sum of the frequencies in n are the same thing, and minus 1. Okay? But that's because we're dealing with sample data now. So we'll work through these examples, and I'll kind of stop and we'll kind of review, see if there's any questions. So if I'm just wanting to calculate the mean, right, I go through every observation, use that midpoint, so 37 times 4 is 148. 40 times 15 is 600. 43 times 25, 1,070. I do that for every observation. I then add them all up, and I get that numerator of 2,795. Okay. I then divide by n, which was really the number of observations in that original data set before it was grouped. But I know I can always find n. If I wanted to, I could just rewrite this as the sum of my frequencies, right? So those frequencies add up to 65. Okay? Any questions on this? Are we okay with this? So we actually end up getting the mean here is exactly 43. So it probably is going to be around there, but it just happens to be exactly 43. So I can now use this mean to calculate the variance, right? So how was I finding the variance? Well, I found the deviation from that mean squared and then multiplied it by whatever my weights are. Here are their frequencies. I did that for every observation. I then remember this summation sign means add them all up. So for the very first observation, I'll take that midpoint of 37, subtract the mean, which we said was what? 43. So 37 minus 43 is -6, squared is 36, times the frequency of 4. 4 times 36 is 144. Next observation, take the midpoint of 40, subtract the mean of 43, -3 squared is 9, multiply by that frequency of 15, you get 135. Now notice for this middle bin, its midpoint is 43, so when I subtract the mean, 43 minus 43 is 0, squared is 0, 0 times anything is 0. And the reason why is because what we're really doing is capturing, even with the weighted variance, similar to the regular variance, the interpretation is, on average, right? How much does the data vary from this middle point, right? Now we're weighting these different bins by whatever the frequency is so that they impact that weighted variance a little more or less depending on whether or not they have a higher or lower frequency. But this bin here is evidence that there is not variation from that middle point, right? And so it adds a 0 into the numerator for our weighted variance. However, these other bins are observation that there is some variation from that middle point. And so when we add them all up and then divide by the number of observations, we're kind of getting this average deviation from the mean squared, right? This average variation from that middle point of the data, okay? So we have our, once we add up these deviations squared times the frequencies, that's our numerator. The sum of our frequencies, that's kind of our denominator. So 522, sorry, I said it's our denominator. It's the sum of the frequencies minus 1 because we're dealing with sample data. So 522 divided by that total number of observations minus 1 will give us our weighted variance. Okay? Any questions on that? Okay with this? So what if I wanted the standard deviation? What's the only other thing I'd have to do here? If you remember from last class or the last couple classes. So if I want to go from the variance, which we have here, to the standard deviation, I simply take the square root. Yep. And that'll apply to anything. So anytime we're looking at a variance, if we want to get a standard deviation, just take the square root. Whether or not it's a weighted variance, we'll talk about some other statistics later on that are different types of variance measures. If we ever want to go from the variance to a standard deviation, we just take the square root. Okay? So that shouldn't be too bad. It should be very similar to kind of what we did last class, right? The only different spin is that we're using midpoints and our weights are frequencies. Other than that, the procedure is really the same, okay? So we're okay with this. So next thing we're going to talk about, we'll talk about it here. We probably won't use it as much as some of the other things that we've discussed throughout the course, but I know you'll see this in different courses. I think specifically marketing likes to use these. But we'll talk about how we calculate percentiles, right? So I'm sure, a lot of us are maybe have encountered or familiar with percentiles in some regard. So a lot of times on ACTs or SAT scores, it's probably your experience, they tell you what percentile your test score was, right? So they might tell you that you're in the 80th percentile, right? So what that means is that your test score was better than 80% of the other test scores. So kind of think about whatever percentile we're interested in, it means that value is above 80% or whatever that P% is of the other values. What it also means is that, and you can get, it's 100 minus that is the percent of the observations above that value. So if I'm in the 80th percentile, 80% of the scores are below me, 20% of the scores were above mine or higher than mine. So we can think about it kind of both ways. Oops, sorry. And I don't think that's anything wildly new to you guys. I think that's a pretty easy concept. But how do I find these percentiles? So I always some people are familiar with this chart or have seen this at the doctor's office, right? They tell you at what ages, height and weight, what percentile were you in, right? So how are they coming up with these lines? Well, basically, I think the easiest way to think about this is, let's say I have 100 observations, right? Now, 1 through 100, those are my observations. Those aren't the values, but I have, 100 observations. They might be, range between 50 and 60,000, right? They're all values somewhere in that range. So what I'll do, if I arrange those from smallest to largest, right? The smallest value would be in the first position. The next smallest value would be in the second position, all the way up to where the highest value would be in the 100th position. So there it's kind of easy to think about, well, what values in the 90th percentile? Well, whatever value is in that 90th spot, right, is above 90% of the observations below it and below 10% of the observations above it. Yeah, show a question. Okay, you're fine. So how do I actually do that though when I don't have kind of this nice idea of 100 observations or the values are a little bit hard to figure out? So I already mentioned the easiest way to do this is arrange the data from smallest to largest, right? You can now give every single value, every observation, a position, right? It's the lowest in the first position. Next lowest is in the second. We can then use this formula to identify what position the value that will give us our desired percentile is in. So maybe I want the 80th percentile. I've got, I don't know, 352 observations. So I plug in N352. I want the 80th percentile, so this P is 80. This formula will tell me what position the 80th percentile value is in. Right? So maybe it's in the, I don't know, 280th position. So I've got my data arranged from smallest to largest. I go over all the way to that 280th position. Whatever value is in that position, that's the value that's my 80th percentile cutoff. Okay? Now it's kind of easy if this is an integer, right? I think I just said 280th position, right? So I just went over to the 280th position. Whatever value is in that position, that's my 80th percentile. The issue becomes, if it's not an integer, right? Let's say it was 32.5. That was my position that this formula told me. There's no 32.5th position, right? There's a 32nd position, there's a 33rd. So we don't simply take the average there. We're going to do something called interpolation. Okay? And hopefully we'll see how this is kind of related to what we've been talking about. So let's say I have this example where I want the 25th percentile and I've got 10 different metal funds, right? So this is how much they're worth. So I've got these different funds. I've arranged them from smallest to largest. The next step is use this equation to find out what position would give me the value for that 25th percentile. Okay. So I plug in my number of observations 10, the percentile I want, which was 25, and I get the position is the 2.75th position. Well, I have a second position, I have a third position, I don't have a 2.75th position, right? But how can I use this to still find the value? Well, if I would have gotten, let's say I would have gotten the integer of 2. Well, then the 25th percentile would have just been the value that's in the second position. So it would have been negative 7.34 is the 25th percentile cutoff value. But I didn't get 2, I got 2.75. So what we're going to do with interpolation is that we know that we're going to be a little bit closer to one integer than we are the other. So here at 2.75, which position am I a little bit closer to? That third position, right? So I don't want to simply take the average of these two values. I want to weight this value a little bit higher, right? Because I'm a little bit closer to that third position value. So what I'll do is I'll look at this decimal to figure out what my weights should be. Whatever the decimal is from this formula, I'll use that as my first weight, so 0.75 here. My second weight will be whatever would get me to 1. So we're going to be between two values, so I need two weights. The first, one of the weights will be whatever the decimal is, so 0.75, and then the other is whatever gets me up to 1. Okay? So I would use 0.75 and 0.25 here. Now, I'm a little bit closer to that third position, so I'll use the higher weight, the 0.75, and multiply it by the value in that third position, and then add to that the lower weight of 0.25 times whatever value is in that second position. Right? So it's kind of like we're not just looking for directly in between, we're kind of looking a little bit closer to the position that we're closer to by using those weights. Yeah. Yeah, so the way I figure out these weights is I simply, once I've entered my percentile and my number of observations into this formula, whatever it tells me, the weights are going to be my decimal. So 2.75, 0.75, and then 0.25 would be my weights. If this was 2.3, my weights would be 0.3 and 0.7. If it was 2.9, 0.9, and 0.1. So I look at that decimal to determine the first weight, and the second weight is whatever would add up to 1. Right? So what that would look like is I take that 0.75, multiply by 8.09. The other weight would be 0.25, multiply that by the -7, and I get about 4.23, which makes sense because I should be a little bit closer to the value that's in that third position than I am to the value that's in the second position. So 4 is closer to 8 than it is to -7. Any questions on this? So the other one that's a little bit tricky and I'm actually just going to edit this, this slide as we go. Let's say instead this was 2.3. So what would my two weights be? 0.3 and 0.7. But now I have to be careful because I don't just simply say, okay, change this to 0.3 and 0.7. It's not the order of the weights. We would want to use the higher weight on the position we're closer to. So here we're closer to the second position. So we actually take the value in the second position, and that gets the higher weight, right? So we identified the weights were 0.3 and 0.7, but we want to make sure the position that we're closer to, which is now the second position, we want to make sure that value gets the higher weight, okay? And this doesn't equal 4.23. I don't know what it ends up being, but this is just the idea that if something was a little bit different, that's how we would assign the weights, okay? What would be a real easy one? What if I got a 2.5 here? My weights would be 0.5 and 0.5. Each one's getting weighted the same amount. What you're really doing there is just taking the average, right? You're smack dab in the middle between these two values. So that's an easy one. It doesn't happen very often. The other thing I want to mention here is, you know, we can think of this, we're using weights, but in these other weighted means, we always had to use our weights and then divide by the sum of the weights, right? So why am I not dividing by anything here? Well, what should these weights always add up to? The way I described, how do you identify them? You look at the decimal and then whatever gets you to 1. So they should always add up to 1. If I divide by the sum of the weights, but the sum of the weights is always 1, does that change anything? No, divided by 1 doesn't change. So theoretically, technically, there is a denominator here, which is the sum of our weights. But if the sum of our weights is always 1, we can really just ignore that. Okay. Excuse me. Any questions up to this point? All right, so we're okay with that. What we got in time? Cruising here. So let's say we now know how to find these percentile values. Okay. We could find the 25th, the 50th, and the 75th percentile, right? We'll call these the first, the second, and the third quartile, Q1, Q2, and Q3. Now, the second quartile, right, think about it, it's the 50th percentile. So what that means is it's a value that's higher than 50% of the data, but lower than the other 50%, which is literally the definition of our median, right? It exactly splits that data. So that second quartile is also, we can say, is our median. We then find this thing called the interquartile range. It's just going to be the difference between the value of the third quartile and the value of the first quartile. We can then come up with these upper and lower limits, go 1.5 times that interquartile range below the first quartile, that'll be our lower limit. Go 1.5 times our interquartile range above the third quartile, we'll call that our upper limit. If we see any data outside of this lower and upper limit, we can call it an outlier, right? So this is called the Q test, right? So you don't have to worry about kind of writing this down too much. We'll go through an example right here and we'll kind of see all of that again. So I just want to give a visual to all that because that's not very appealing to the eyes, right? All right, let's see if there should be a remote here, but this isn't auto-focused. Well, hopefully it's focused enough. Oh yeah, it's not too bad. So just as a reminder, we've got our interquartile range here, which is the difference between the first and the third quartile. So you might see these in other classes. They're called box and whisker plots, right? So all you do, and there's a thing in Excel you'll see them too. You might have, I feel like they use these in science classes in high school, but I could be wrong. So the first thing you'll do is plot where your second quartile or your median is. Right? So let's say, I don't know, say this is 50. You then draw a box where this is your third quartile and this is your first quartile value. So maybe this ends up being 40, and I don't know, maybe this ends up being 70. Right? So notice that first quartile is a little bit closer to the median than that third quartile is. Okay? what you then do is say, okay, I can go from that third quartile and find my upper limit, and then go down below your first quartile to find your lower limit. Now, how do we do that? This was, you take that third quartile and add 1.5 times our interquartile range. And then to get the lower limit, we took that first quartile. Oops, sorry. This should be a negative sign. And you subtract 1.5 times that interquartile range. You know, so if we do that math here, our interquartile range, the difference between our first and third is 30. Okay. So 1.5 times 30 is 45. So go 45 below first quartile. This would be -5. You go 45 above the third quartile, that gives you 115. Okay. So this would be how you kind of build or design your box and whisker plot. You really just have to find the value for these 3 quartiles, and then from there it's just a little bit of extra math, right? But once you have those percentiles, 25th, 50th, and 75th, just a little bit of math and kind of drawing up the graph. Now, the reason why I show you this is because it kind of gives us an idea about where the majority of the data is. You know, if our median and our first quartile are pretty close in value, that means there's a lot more values really close to the middle of the data below it. And then the values that are above the middle of the data, they tend to kind of be much more spread out further away. So we might have kind of like a longer right tail. But the real important part is this upper and lower limit allows us to identify outliers, right? So I could plot all of my data against this, right? I could say, you know, there's one observation that's, you know, I don't know, 61, one observation that's 52, another observation is 41, another observation is 10, another observation is 85. And I could just go ahead and I plot every single data point that I have, right? Any data point that is outside of this upper and lower limit, we say we're using this to identify these as outliers, right? And potentially, you know, they vary enough from the majority of the data that when we actually calculate some statistics, we're going to actually exclude those, right? Because we know these are really going to screw up things like the mean or even our variance, right? So we use this as a test to determine what data points might be outliers. Now, usually, hopefully, we don't have any more than, you know, 1 or 2 outliers, but this would be, you know, how we identify that. Okay. Any questions on that? Shouldn't be too bad. I'm not going to ever like make you build one of these. I just know that other courses will talk about them, and I want to make sure that I've covered that. So let's see if we can get a seamless transition back here. Didn't work out from the last section in class here. Let's see if the screen switches. Did I kill it? There we go. So we've got kind of building this box and whisker plot, and then we have this test to determine if there's outliers. So please don't reject me as an outlier because you are the Q test. The Q test rejects outliers. I thought that was a somewhat clever meme, so I figured I'd throw it in here. So we can build these pretty easily, and this is kind of still thinking somewhat about the distribution of the data set. Right? So kind of similar to the graphs, I had this whole discussion how, well, we've only been looking at one variable. Now we're going to look at the relationship between 2 and do a scatter plot. Well, up to this point, we've been thinking about just one variable with all these different computational statistics. Now we're going to think about some statistics that tell us the relationship between 2 variables, right? So when one variable goes up, let's call them x and y. As x goes up, y can either go down, y can also go up, or y can kind of stay the same, right? Not do much of anything. I'm going to have 2 measures of whether or not when when x goes up, if y goes up or down or not do anything. And those measures will be called the covariance and then the correlation, or sometimes called the correlation coefficient. Okay? So we'll talk about how we compute both of these. So first, the covariance, right? We're actually going to write as sigma and then whatever 2 variables we're looking at, right? So let's say I have x and y. Sigma xy is the covariance between our x and y variable. If it was up to me, we would write this as sigma squared xy because the fact that it's called the covariance, but we kind of notate it with a standard deviation is a little confusing. But the covariance, we'll kind of write this as sigma, and then between whatever two variables we're looking at. So what we're going to do with this covariance is go through every observation and say, okay, for this x variable, and we'll use height and weight for now because that's the example that I show you in a second. Let's say our x variable is height and our y variable is weight. We're interested in, is there a positive relationship? As height goes up, do we tend to see weight go up, weight go down, or just not really kind of unimpacted by it, right? Do people just get stretched out as opposed to like building more bone and things like that? So we'll go to the first observation, say, is that person above the average height? Or is their height above the average height? Right? Whatever that difference is, we then multiply that by, are they above or below, or what's the difference from that average weight, right? If they both are on, right, if someone was above average height and above average weight, we'd have a positive times a positive, and a positive amount will get added to that numerator. Because that one observation was evidence that they tend to be on the same side of the average. When someone is above average height, they also tend to be above average weight. If we had a person that was above the average height, so this deviation would be positive, but they were below average weight, this would be negative. A positive times a negative is a negative, because that observation was evidence that when someone tends to be above average height, they are below average weight. Now that was just from one observation. We're trying to get what the average relationship is across every single observation. So we'll do this for every observation, add them all up, and then to kind of get that average, we divide by the total number of observations, right? So the covariance you can think about is kind of like the average evidence of whether or not they're on the same side, these two variables are on the same side of the average or on different sides of their respective averages. It's kind of throwing a little bit of a weird wrinkle. And I'll go through an example with the actual data set here in a second. The sample covariance is the exact same thing. We just divide by n minus 1 instead of n. Same kind of concept as the variance, right? So here's our two covariance equations, right? But what does this covariance actually mean, right? Well, think about it when I said if someone's above average height and above average weight, positive times a positive, we get a positive amount added here. And that's because that was an observation that provided evidence that these two things are on the same side of the average more often than not. Right? So if I have a positive covariance, that's telling me that when height is high, weight is also high. That they have a positive relationship, right? They move, they both tend to be on the same side of the average. If it was negative, right, the covariance I calculate is negative, that means on average, these two variables tend to be on different sides of the average. When one of them is low, the other tends to be high. And then if I get something that's close to 0, there's really just not a lot of evidence that these two things are correlated at all. So, you know, if I get something that's 0, it's probably because there was a lot of observations that height and weight were on the same side of the average, but there was also a lot of observations where they are on different sides, and they all kind of canceled each other out. Because unlike the variance, with a covariance, these values that get added to the numerator can be positive or negative, right? So certain observations, right, would provide evidence that they're both on the same side of the average. Other observations gives you evidence they're on different sides, and they all kind of cancel each other out if you get a covariance close to 0, okay? Any questions on this before we kind of keep moving? I'll show you an example here with some numbers. But I just want to make sure.
I just had a quick one.
Yep.
So would it be right to say that this tracks correlation between variables then?
Yeah, so you're beating me to the point here in a little bit, but the covariance is a measure that we will need to calculate the correlation. But if you want to think about it, the covariance is some measure of how these two variables are correlated. Yes, you can think about it that way.
Okay, thank you.
So I want to be careful with our words because we have another statistic we'll talk about in a second, which is literally the correlation coefficient, right? And we'll see kind of the difference between that and the covariance here in just a second. Yep. Yeah, it's kind of telling you like what the average relationship is between these two variables, right? So let's say we had a data set where we had some actual height and weight values. So you can download a bunch of different type of data from the CDC. This one had height and weight in it, and it was big, so I downloaded it. You can calculate, you can imagine if I had this in Excel, very easy to come up with what the mean is, right? Equals average, highlight the entire height column, equals average, highlight the entire weight column. I now have my average height and my average weight. So what I'll do for every single observation is first, how much does its height deviate from the average height? How much does that person's weight deviate from the average weight? And then multiply those two differences by each other. Once I do that for every single observation, I would then add them all up and divide by the total number of observations I have here. Okay? If this is population data. If it's sample data, divide by the number of observations minus 1. Okay? So let's think about it. This first person, right, is above average height, but their weight is below the average weight, right? So they're above average height, but below average weight. So this one observation was evidence that these two things tend to be on opposite sides of the average. Or that when I see this person who's a little bit taller, they tend to weigh less. So this is evidence that maybe there's a kind of negative correlation or a negative relationship between these two variables. So it adds a negative value to my numerator, right? Or to my covariance. Now the next couple observations provide evidence that, well, this person, all three of these people are actually below, this one's just barely below, but they're all below the average height, right? So that difference from the average height, we get negative values. They also are all below the average weight. So when I multiply their height and their weight are both on the same side of the average, they're both below the average. Negative times a negative is a positive. These were three observations that provided evidence that these two variables tend to be on the same side of the average. That when height is lower, weight also tends to be lower. So that there's a positive kind of correlation between these two variables. They tend to be kind of move with each other. Now, we would have to go, these are just 4 of the 44,000 observations. We have to go through every observation and then kind of take the average relationship between these two variables. Right? Any questions on that? Does that make a little more sense, kind of seeing the data, how you actually go through and do this by hand? Okay. So if we do that, we end up getting to 76 is the covariance, right? Okay, that's great. But what the hell does that mean, right? How do I use this? Well, the sign tells me that there's a positive, on average, there's a positive correlation between height and weight, right? But how strong is that? Like how big can the covariance get? Is like 100 the highest? Is 10,000 the highest? Also, what's the units, right? I have inches as my height variable and pounds, but I'm multiplying them, so my units are now inch pounds. Like what's an inch pound? I can't. How do I compare an inch pound to, let's say I wanted to look at the covariance between years of education and income? Well, there my covariance would be years times dollars. So year dollars and inch pounds, I can't really compare across those two, right? So what am I going to do? Well, this is a good way to kind of measure that the variation that exists from the average for both these variables. Well, you can imagine, right? If I think about something like height, what's like, I don't know, let's assume the average person is, I think it was 5'4" here. This had to have been a lot more females in the data set, but let's say average height is, just to make it easy, let's say it was 6 foot, right? Well, what are the highest deviations you could see in inches? Well, I don't know, maybe someone's like 8 feet tall, but at most that's a 24-inch deviation from the average. So when I start to think about the differences I can see for height, maybe 24 would be the highest one. Well, what if I'm looking at the variable of income? Well, there I can see deviations of 24,000, and that's not even the highest I could see. So inherently, because that income variable has more variation in it, right, just in terms of the values, the covariance is going to be higher as well. So I'll never get a higher, a covariance that's going to be higher than looking at a relationship of income with something, because that original variable is just so much variation. So what we'll do is take this covariance and scale it, right? We'll say, look, this covariance I know is just influenced by whatever the original variation that exists in each one of these variables that I'm using, right? There's some underlying variation that exists in height and in weight. I want to kind of scale this, right? So that I can compare across different types of relationships. I want to compare the relationship between height and weight with the relationship between years of education and income. So when I divide by the standard deviation of each variable, essentially what I'm doing is I'm accounting for this original variation that exists in these two variables. And it's going to work and it's going to scale my covariance. Okay? Now, you don't have to understand the mathematical proof behind why, but that's kind of the general intuition. We're dividing by the standard deviation of each variable to kind of account for just the variation that exists, not just, not because of the relationship between our x and y variable, but that just exists inherently in both of those variables independently. Okay? And I'll give you somewhat of a general math proof. It's not a pure math proof, but it gives you an idea about why this next thing will be true. That once we do that, and here it's just written a little bit differently for the population and sample. Rho, the Greek letter, is the population correlation coefficient. The sample correlation coefficient we write as R. Okay. So once I divide by these standard deviations, my correlation or my correlation coefficient ends up always being between 1 and -1. 1 would be if two variables were perfectly positively correlated. -1, they're perfectly negatively correlated. Right? And then kind of moving towards 0, the relationships get weaker to the point where once we get to a correlation coefficient of 0, there's no relationship between the x and y variable. Okay? Or there's no correlation. Excuse me. So you can kind of imagine, the sign tells us something from the covariance, but once we scale it and get this correlation coefficient, we now have everything scaled so that I can compare across different types of relationships. Because think about it this way. So I had inch pounds here for my covariance. Well, I'm dividing by the standard deviation of height. So I'm inches, dividing by inches, so the inches would cancel. Dividing by the standard deviation of y, so the pounds cancel. I basically get a unitless measure. And then by dividing by the standard deviations, I account for the underlying original variation in the two variables, and everything's going to be scaled between 1 and -1. So I'm going to try to give you somewhat of a glimpse into why that happens if we think about what's really going on behind the scenes here. So we're waiting. All right, there we go. So we started out with my correlation coefficient was my covariance, and then divide by the standard deviation of each variable, right? I can write in the equations for these things. So the covariance equation looked like this. And then, I don't know, we divided by, here I'm using the population, so I guess I should technically write this as mu of x and mu of y. We'll then divide by the standard deviation of each variable. So we've got the square root of the sum of x minus the mean of x squared over n times the square root of the deviations from the mean y over n. Right? So you can kind of imagine, once I divide this, I've got n divided by the square root of n times the square root of n. You can kind of imagine how those are going to cancel. You can kind of see here, well, I'm taking the square root of things that are getting squared. So you can kind of imagine how that cancels. I then have the difference between x and the average x times the difference between y and the average y. I've got that up here. Now, that's not the perfect math because these summations do some different things. You can kind of imagine how, like, if there was this perfect correlation, everything would cancel there so that you would get 1, right? Now, the mathematical proof is a little bit more in-depth as to why when we divide by this, we're actually scaling that covariance. But that's the general idea. You can kind of see that there's similar components in each one of these statistics. So that when we calculate that correlation coefficient, it does end up being between 1 and -1. Okay? All right, so that's just I just want to kind of give somewhat of an insight. We don't have to have a perfect understanding about exactly why that occurs, but we do have to know that that is going to be the case. So let's say I come up with a correlation coefficient between height and weight in a second here once we get our screen back. There we go. So let's say I go ahead and I compute that. I get my covariance. I plug that in. I get my standard deviation on each one of those height and weight variables. I plug those in, and I get this correlation coefficient of 0.45. Once I have my covariance and my two standard deviations, this is pretty easy, right? I just plug them in to get my correlation coefficient. In fact, we probably won't have time to go through the examples today, but I put 2 questions up here in the slides that if you want a little bit of practice, one of your online quiz questions will look very similar to this. But it's really just plugging in your standard deviations and a covariance once it's given to you. You're just plugging them into this equation, which is, I think, relatively easy. So we get this correlation of 0.45, or it's telling us that as height goes up, weight tends to go up as well, right? There's this positive correlation between the two. But I can now use this, and let's say I come up with a correlation coefficient between years of education and income, that's 0.7. What I could then say is the relationship between years of education and income is stronger than the relationship between height and weight. And in fact, this 0.45, how strong is it? Well, I mean, 0 is no relationship and 1 is the strongest, so it's like kind of in the middle, right? It's not real strong, but it's not real weak. That being said, when we want to make statements about like two variables being highly correlated, we usually like want to see like 0.7, 0.8 or higher, right? So this isn't a super strong relationship, right? I think intuitively we know it has to be positive, right? Like a 5-foot person versus a 7-foot person. I mean, if the 7-foot person weighs less, they're not going to probably be in very good health. So, you know, but if we work out the actual numbers, we do end up with a moderately positive relationship there between those two. Okay. And if you know, another way you can think about this is like, I can compute this statistic so that I can compare across data sets. But right, if I would have done a scatter plot, it would have been pretty obvious that height and weight look like they have some kind of a positive relationship. Like the slope isn't super steep, but if I did a line of best fit here, it looks like it would be a positive relationship. But exactly, you know, how strong is that correlation? That's what we can compute calculating the correlation coefficient. Okay. Any questions on that before we keep moving? Okay. Like I said, you know, these are really, you know, all I'm doing here is taking the covariance and dividing it by each one of these standard deviations to come up with like what that correlation coefficient is. So these are just two examples of that. I'm not going to kind of hammer these too hard. I think next class I'll start out. We'll talk a little bit more about this idea of correlation. Preview some stuff we'll do actually towards the end of the semester. I think we should have time. Might watch this little video. It's kind of fun at the end of class, next class. But then we'll start on probability. So I'll introduce probability on Friday. I'll likely get a Learn Smart up there that I want you to read next week for some of the more in-depth probability stuff that we're going to talk about. But I'll kind of gradually ease us into it. I don't know. Some people, it's a different way of thinking once we get to probability, and so that subject kind of gives some of us a little bit of trouble. So I try to go into it real slow so we get a real good base understanding. Okay. So you've got that Connect assignment, you got that Excel assignment. Start working on those. Get as much work out of the way this week as possible, so you can ask questions next week before it's due. I'll be available. Send me an email if you want the time to meet. Other than that, once again, we have a lot of empty seats, so if you want to come to class, I highly encourage you to. Otherwise, I'll see you guys on Friday.